thank you folks for being there. I really wish I could be there in person with you as well. I had planned to be there in 2020. I had planned to be there again today in person. Unfortunately, my family had a COVID outbreak within our household the day before I was supposed to travel. Hence why I'm stuck here instead of being there with you folks. I really wish I was there in person with you all. But are you all having fun so far? Awesome. Cool. All right. Well, let's go ahead and get started. My name is Jeff Handley, for those of you that I haven't met yet. I work at Microsoft, and I'm on the .NET team. I've been on the .NET team since late 2019. Worked on .NET in Microsoft from 2008 to 2015, took a hiatus to go scratch and itch, working with React and doing some front-end stuff again. But I've been back at Microsoft since December of 2019. Like I said, I'm a member of the .NET team, particularly on the .NET Libraries team. And today I'm going to talk to you about one of our exciting new features in .NET 7 called generic math. So kind of start out, what is generic math? What can it do? We're going to talk through a lot of that stuff by way of showing code. I'm going to jump into Visual Studio in a minute. I'm going to walk through some live coding. Forgive me, I'm going to use some snippets to save you the keyboard clacking. But I'm going to answer those questions of what is generic math by showing you how I use it, how it can be used. And I'm really hoping it will spark some thoughts from you folks in terms of how you can use generic math on the business applications that you work on and the libraries you build. After we do some demos, I'm going to show you a sampling of the APIs that were introduced as part of generic math, and then talk a lot about the other features that were built out as part of delivering generic math to .NET 7. This has been a multi-year endeavor, about 2.5 years we've been working on this feature, and there were a lot of other features that we needed to pull off across the language, compiler, runtimes, JIT, cross-gen, etc., in order to open up these new APIs from the .NET libraries. So we'll talk about how those APIs were designed and what they're shaped like. And then at the very end, I'm just going to show a couple of small examples of how .NET internally is using generic math, how we've started to refactor some of our own code to use these new patterns and practices. So like I said, I want to dive right into Visual Studio. I've got a math helpers demo here. Pretty straightforward. We're going to use standard deviations. The idea behind this is to show some code that you've probably written yourselves over the last 20 years. You've wished it was easier to write. You've probably even wondered why this function isn't part of .NET in the first place. We're going to look at what that looks like traditionally, and I'm going to show how we can rebuild that using the generic math feature. So let's run this demo real quick so you can see what we're going to pull off. It's just a console application. When we run it, we're going to get the output of a bunch of different types. The primitive types, some primitive numeric types from .NET. And for each of these primitive numeric types, we're feeding it a sample of data, and we're going to, and we print out the standard deviation of that sample. So that's what you can expect to see from this code. Now let's take a look to see how this is happening. And again, this is before using generic math, traditional code that we've all been able to write for the last 20 years. If we dive into get standard deviations, this is just a helper function for returning a tuple of a bunch of different numeric types and a calculation of standard deviations over those. And I've got just a bunch of static fields defined for my ranges. So we've got signed bytes, we've got uints and longs, and I'm just feeding it, min value 0, max value across each of these types, just to give it a sampling of data for them. If we flip back and we go in here again and we dive into our calculate standard deviation, this is probably code you've written. Does this look familiar to you? We're taking an IEnumerable of S byte of values, whether or not it's a sample. And then we've got the standard deviation implementation here. We're going to check the count. We're going to make sure we've got 2 or more items. We're going to build up our accumulator. and start doing the standard implementation of a standard deviation. We've got an inline mean function down here that also is tied to this specific type of input, these S bytes. It's going to return a double, and then our standard deviation ultimately is going to return a double after doing some math here, right? We've got the mean, we've got a subtraction, we've got squaring or multiplication, we've got addition for our accumulator, then we've got some more division, ternary, and performing a square root at the end. Now, this is the overload for S byte. But you can see this same block of code has to be repeated over and over for every type of input that I want to support for my numeric types. This is really annoying. It has been. You could probably think back to when .NET generics first crossed over your fingertips. When you first saw that for the very first time, you started implementing code like this, and you wondered, why do I have to keep doing this? Why do I have to overload for all these numeric types? Why isn't there just some abstraction over numbers? Well, there were a lot of reasons why we couldn't pull that off in .NET before, and that's what we have done in .NET 7. So I'm going to edit this demo here. We're going to add a couple of new items. We're going to add a calculate generic .cs, and we're going to add a get standard deviations generic.cs. In our calculate generic, I'm going to, again, save some keystrokes here. I'm going to grab a snippet, but we're going to walk through it. Oh, shoot, I've got to write quickly. Well, hold on. Let's walk through and figure out what's going on. So we've got a new standard deviation of t. The standard deviation of t is now accepting an IEnumerable of t values instead of a byte or an int. We're still taking the same as sample bool. And then we've got a type constraint here of where t is an I number of t. And that's what can't be found. I number of t is actually one of the new APIs introduced in .NET 7. I forgot this project is still targeting .NET 6. We're going to have to do a quick upgrade. Shouldn't take too long to upgrade from .NET 6 to .NET 7. In fact, we're done. If you hadn't caught the news, .NET 7 was released earlier this week. Changing a project like this from .NET 6 to .NET 7 is exactly that easy. I hope you'll install and start updating your libraries. So now we've got standard deviation of t, IEnumerable of t values, and we're constraining t to be an I number of t. This is one of the key new interfaces for generic math. It defines a number type. This is an interesting pattern where t is an I number of t, so it has to be a self-constraint against its own type. But now if we look closer at the implementation of standard deviation of t, we can see that we don't have S byte or int or anything else dealing with the input value, but we do still deal with doubles. We do this because we're ultimately going to return a double out of our standard deviation. The implementation is exactly the same though. If we look back at calculate, we can see it's the exact same algorithm that we have for calculate generic, but now where we needed to get something from our input type over to a double, we use the new API called create checked on double. The idea here is I take my input value and I'm going to ask double to create a new double from that value. And it's going to do this in a checked context. So if there's an overflow, this number can't be represented as a double, it will throw. So this means it's a robust implementation there. So now instead of all of this code with all of these overloads, we can now just have a single implementation of standard deviation with our inlined mean, and it's abstracted away to the numbers. Now, let's flip over to this next one. Let's implement the new helper for getting the standard deviations of those generic types. So now we've got to get standard deviations generic, and we're going to yield more tuples here, the same types, and we're going to call into our calculate generic standard deviation. So if we look at this, we can see that we're calling into standard deviation of S byte. I've got a couple of types down here that I didn't have previously in our data. Let's go add those. We go into our data here. I want to add a public static read only. A decimal would be supported here as well. In fact, decimal, big integer, all of the numeric types in .NET are supported in generic math. But we're going to add new int 128s. Int 128 was a type that we added also in .NET 7. It's a type that we didn't want to implement until we had generic math in place, so that the implementation of int 128 itself would not have as much repetition. So once we had generic math in place, we were able to implement that within, honestly, a number of days. We're going to also use int 128.0 here in the middle, and then we'll do a max value. And the next one we're going to do is half. Half is a type that we introduced a couple of years ago. It's a half precision floating point. So it has half the bytes of a float. So we've got 128s and halves. And now we can get those there. Let's flip all the way back out to our program, and let's modify this to, instead of calling our get deviations, let's call get standard deviations generic. So now we're going to call into a similar helper function. Now we're getting our generic implementation. We're going to get those results and write them out. Let's give it a run and see how it looks. Boom, there we go. The same type of data we were getting before. We've removed hundreds of lines of code from those implementations. And I'll let you know, when we've been going through the practice of adopting these patterns in .NET Runtime, removing these blocks of duplicated code, we found places where our implementations had diverged accidentally over time. Now, standard deviation is one implementation. I want to show what it's like to use generic math in a different way. Let's create another helper function. We're going to create something called a midpoint. So let's implement a midpoint function here. We'll also put this in calculate generic. I want to do something different with midpoint. Instead of having this use a constraint of I number of t, I'm going to use some of our really granular interfaces that we have in generic math to declare what properties and functions and operators I need to have on this abstraction over a numeric type in order to perform this implementation. So calculating a midpoint of a data type, not of two values, but of a data type itself. I want to know what the min value and max value of a data type is. And I want to calculate what is the midpoint of that. So given an int 32, what's the midpoint of int 32? What's the midpoint of half? What's the midpoint of double? I want to have that expressed by way of an algorithm that doesn't know anything about those types. Now you can imagine this code as a giant switch statement. You might even use some cool pattern matching in order to pull that off. But in this implementation, we're going to take a type t, and we're going to request that this t have min max value, a multiplicative identity, addition operators, division operators, modulus operators. And just from those properties and operators, we can then implement this algorithm for determining the midpoint. Let's flip over to our program, and instead of printing out standard deviations, let's write our midpoint data. So we're going to start off with half. We're going to calculate the generic, the midpoint of half. We're going to write out to the console what the min value was, what the calculated midpoint was, what the max value was, and then we'll print out some data just to confirm that we've calculated the midpoint correctly. So here we can see, again, that implementation of midpoint knew nothing about half. It only knew of those 5 interfaces that it's dealing with, and we're able to calculate the midpoint of 0. Now we could do this with any other type. Let's change half to be decimal. And run that. Oh, we got an overflow exception. See, we had this case of performing that create checked, and this can throw in those cases. But we can also do things like int 32. Stop that, rerun. Now we can calculate the int 32 midpoint, which is strangely actually -1. Now, this is all well and good for standard types, but there are also places where you want to perform generic math operations or abstractions over algorithms against your own types. And that's really where I see a lot of the value in generic math myself. I think back to all the times where I've needed to deal with things like custom units or domain models where I wanted to perform algorithms over them. I kept actually trying to think about what is the standard deviation of a customer. I couldn't quite figure that out, but if you wanted to write standard deviation of a customer, you could just implement those interfaces. Let's do something a little bit more sane than that though. Let's add a new item. We're going to create a weird number. And this weird number is going to be defined as a struct. And we'll skip over the interfaces that we implement here for a second. I'm going to show you the properties of this number. And I'm going to show you there's actually nothing terribly special about this struct. But we're going to give it a min value and a max value. And what we're really going to do here is under the covers, we're just going to have weird number wrap around int32s. Now, you've probably had domain entities yourselves, business entities that wrap around integers, and they need to be a subset of integer values. Again, thinking about units, meters, feet, miles. It'd be kind of nice to implement those units with some rules around what the min values, max values are, performing addition, any place where you've implemented operators yourselves on numeric-like types, you can now start to think about them in terms of abstractions over numbers. This particular weird number implementation is going to set a min value of -10, a max value of 40. We're going to have the multiplicative identity still just be 1. So something times 1 will equal itself. And then we define our plus, division, modulus, and subtraction operators. And those are just operating on the underlying ints under the covers. So now that we have a weird number, let's flip back over to our program. And instead of showing the midpoint for int32, let's show the midpoint of a weird number. Again, we've got a range of -10 to 40 on our weird number. That calculates a midpoint of 15. My algorithm of midpoint knew nothing about weird number, knew nothing about my domain model, but it's able to operate over it as though it's an abstraction over any other number type. So with that, I hope that you can start to think about how generic math can be used in your code. You can think about the coarse-grained I number of t, and also think about those fine-grained or granular implementations of algorithms, such as this, where a weird number just needed to advertise that it is an I min max value, an I addition operators, multiplicative identity, division operators, modulus operators, and subtraction operators. Whatever set of those interfaces that makes sense for you to expose in your type, you can do so. And then algorithms that need those operations can constrain types of T down to that. So I want to talk through some of the APIs that you saw here and how we designed them. The UML diagram should pretty much tell the story. There's a lot of freaking interfaces here. We had to touch a lot of types to pull this off. In fact, over 30 interfaces were introduced. And this is the first time we've ever introduced new interfaces that we then applied to the primitive types, such as in 32. I mentioned coarse-grained and granular or fine-grained interfaces, and that's really the spirit of generic math, is we really had to pull off those two different universes. We had to make it easy to have types implement the subset of operators that they use and be able to have methods that use those constraints. But then we also wanted to have the general concept of what is a number, I number base, things like that. This design is something we spent 2.5 years putting this implementation in place, but well before that, we've been thinking about what generic math would look like. And benefit for us, we had some existing ecosystem momentum that we were able to draw influence from. So Swift has numeric protocols, Rust has op traits. We validated our design by comparing against those two ecosystems as well. And that helped us understand that we were on the right track with these interfaces. We shipped preview versions of them in .NET 6. A lot of folks started building against them. We got a lot of feedback. It was really exciting. And then we refined these APIs in .NET 7. If we zoom all the way out to the coarsest grained APIs, the ones that are the largest, we've got a few or a handful here that are pretty notable. Just like anything in .NET, we're probably gonna have a base. So we've got an iNumber base of T-self. An implementation of this is int32 implements iNumber base of int32. And what that means is iNumber base has a bunch of static abstract interface members defined on it that then must all operate as int32 operations when applied to the int32 type. Deriving from iNumber base, we have iNumber of T-self. We have binary number, binary integer, floating point, IEEE 754 floating points, and then IEEE 754 binary floating points. As a peer to iNumber, we also have signed number and unsigned number. And all of the numeric types across .NET take some combination of these where applicable. There are some number types that aren't signed or unsigned. There are some that are binary, some that are floating point. And then we also have the very fine-grained interfaces that we mix in with these as well. We've got a pattern here over all these operators and properties and functions where the interfaces use a pattern of T-self, T-other, and T-result. You're going to see that in the documentation. You're going to see that in the code samples a ton. I've abbreviated that here on the slide as self-other result, but you always see it as T-self, T-other, T-result. What you can think about this as is left-hand side, right-hand side, and what's the result. So int32 plus int32 equals int32 is going to be an I addition operators of int32 and 32 and 32. So int32 will implement I addition operators of int32 and 32 and 32. It is possible to mix and match those. We've got places where we're using things internally where other will be a different type, or the T result would be the desired output type. If we go back to our standard deviation implementation, in fact, let's flip over to that and show just quickly what that could look like. If we look at our calculate generic, we wouldn't necessarily need to have standard deviation return double now. We could have standard deviation take a T and a T result and return a T result. And then instead of building up doubles as our accumulator, we could start to create whatever the desired output type is and constrain our T result to be an I number of T result. Oh, dun, dun. So now we can start to get to things like .0. Well, that was going to do it for me, and I skipped it. T result .0. And here we're going to need to do the same thing of T result create checked over the mean. You can get the idea here. I won't finish this out. We'll jump back, but that would allow me to go into my standard deviations, and I can now say here that I want to give in S byte and get back out double. Or I might have an operation where, you know what, I don't need that level of precision. I could just get a single or a float out of this. If I really wanted to, I could just get an int back out. So this is now something that you couldn't even do before, having essentially overloaded return types. You could have overloaded input types before. Now you can essentially have overloaded return types in these algorithms as well, and let your caller tell you what level of precision you want for your results. That's pretty exciting. So these other operator interfaces, we've got I addition, subtraction, multiply, division. Now, each of these under the covers is just implementing a single operator. We made it plural in case we ever invent a new type of addition. It could get added into that interface and use default interface methods. But for naming sake, they're all plural. We've got I modulus operators, unary plus, unary negation. Then we've got I increment operators of T self. So this is your plus plus, and I decrement is minus minus. Here we don't need a T other or a T result because we're just going to mutate the value you've given us. There is no other value. It's going to just be the value of 1 for whatever the type is that you've fed in. We've got bitwise operators, shift operators, comparison operators, and I-equality operators. Most of these, like I said, have just a single operation. The bitwise, shift, comparison, and equality, you're going to see more members on those interfaces. We also have function and property interfaces that get defined for these details. So these also use the same pattern of T self, T other, T result. So we have the I additive identity. This means, what number can you add to a number and have it not change? So 0. The multiplicative identity we saw is usually 1. What number do you multiply by something in order to get the same result? We're going to multiply by 1 there. We saw I min max value. Then we have these function interfaces for exponential functions, power functions, root functions. So square root is sitting on I root functions, trigonometric, hyperbolic, and logarithmic functions. So now you can start to think back to the implementations you've had of your business models and your business-specific algorithms. Start to think about what mathematical functions did they need in order to pull off their functionality, and you can model them in terms of which interfaces you would need to constrain to. So at a high level, that's what you're going to get from generic math. Take the hundreds of lines of code, deduplicate that down into a standard generic-based implementation. Like I said, you might be wondering, why couldn't we do this before? We've had .NET for over 20 years now. We've had generics for coming up on 20 years. But there were a lot of things in the way. So let's talk through what some of those other features were that came out as a byproduct. First, and probably most important, is a new language feature for static abstract interface members. The idea here is to be able to define an interface of T where T is constrained to be an implementation of that same interface of T. This is known as the curiously recurring template pattern. If you've used C++ templates, you've probably seen this for the last few decades. There are some other places where this same base and derived class sort of recursive referencing of one another comes up. We're solidifying this pattern in this static abstract interface members scenario, where in this case of I of T, where T is I of T, we can now have static abstract members on an interface. You might wonder, isn't abstract on an interface a bit redundant? I kept asking that question myself, but we do want to leave the door open to have static abstract and static virtual members on interfaces. In fact, we can do static virtual members where you have default interface methods defined. So in this case, we do specify that this is abstract, meaning there isn't an implementation here on the interface itself. But in order for a type to implement this interface fully, in addition to any instance members that the interface defines, you must also implement static methods. Now, stepping away from generic math for a second, one of the cases where I'm really excited about static abstract interface members is for factory methods. Think about how many times you've written code where you constrained T, and you could constrain it to have a constructor, where T has a new that's parameterless, but you couldn't constrain T to have a method that was static that you needed it to have in order to call into some factory. You can now start to use static abstract interface members to define factory interfaces. So things like double dot create checked that you saw there, that's essentially a factory method of double saying, yes, I'll have a static method called create checked where you can hand me any other I number base, and I'll create a double from it. It's a factor method. In order to pull off this feature of static abstract interface methods, we had to design the language feature. We had to get the compiler working against this. We had to integrate with the JIT, cross-gen and cross-gen 2 for cross-compilation, for multi-targeting. In fact, the reason why we had to do this in both cross-gen and cross-gen 2 is .NET 6 was released with everything built against cross-gen. We started migrating over to our cross-gen 2, our re-implementation of cross-gen during .NET 6, .NET 7, which meant we had to support static abstract interface members on both sides of that migration. We had to update the core CLR and mono runtimes. And then the type loader performance is notable down here as well. We think about the 30 interfaces that we were adding into system private core lib or system runtime. We're adding those interface implementations to all of those primitive types. Now, in order for the runtime itself to spin up, we have to load all the API information, all the type information about all of the primitive types, such as in 32. The runtime itself can't run without those types being defined. And you've probably seen and heard that we've been paying a lot of attention to performance in .NET. We made .NET 5 faster than any version of .NET before. .NET 6 is even faster than .NET 5. .NET 7 is even faster than .NET 6. Every year, we're trying to squeak out every bit of performance that we can from startup and execution time. The idea of loading 30 additional interfaces on all of our primitive types was going, at first, it was going to add multiple seconds to the startup of every single .NET application in the world. So we had to do some heavy refactoring under the covers in our type loader to make it load these interfaces very performantly. And we ended up with the net result of better performance for app startup in .NET 7 with generic math than what we had in .NET 6. Beyond the language feature and all those layers having to support static abstract interface members, the next feature we added were checked operators. Now, you've been able to define operators such as plus, minus, 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 modulus. You've been able to define these since the beginning of time. But something we've never allowed in the language was for you to essentially overload an operator by specifying how it performs in a checked context versus an unchecked context. In an unchecked context, an operation might overflow and result in wrapping around to the other end of the spectrum, whereas in a checked context, an overflow needs to throw. All of the primitive types that we had in .NET all had logic specific to that. And in fact, the .NET runtime itself knew the constraints of those primitive types, knew which operations could or should not overflow, and it knew when things, when to throw and when not to. We didn't have a way to express that in the APIs themselves. Int 128, interestingly, we kind of have this catch-22 where we wanted to introduce int 128, and we wanted to do that on the library side without having to go implement something in the compiler and the runtime for it to even know that int 128 exists. But we didn't have a way to do that because the runtime itself needed to understand what the checked constraints were around it. So we added a language feature to be able to overload based on checked, and we used that in int 128 ourselves. In the .NET libraries, we implemented that in a matter of days, and the runtime didn't have to be aware of that type being conjured up. So this is something if you're doing really low-level mathematical operations and you need to deal with checked and unchecked constraints yourself or those contexts yourselves, now you can overload your operators based on check. We also needed some updates to our shift operators. The first was the right-hand side of shift operators. All the way back to the beginning of C#, we've always mandated that whatever value is on the right-hand side of a shift operator was always an int. It was just arbitrary. Of course, you're going to shift by a number of bits, and that number is probably going to be an int. It wouldn't make sense to shift the right-hand side by a string. We've all seen cout getting the right shift with the string, and it does weird things in C. It didn't make sense. But when we think about numbers as an abstract concept, they're not necessarily numbers. We wanted to relax that so that you can use these functions however you need. We also needed an unsigned right shift operator within some of our own implementations. So we've always had the double greater than for a right shift, and we can see the results of that down here, where we're going to take these ones and we're going to shift right a couple of bits here. So these two ones move over. And the result of a traditional right shift is that we saturate those high order bits with whatever they were before. So this one remains, we continue to shift over, we replicate that value. An unsigned right shift introduced in C#11 is a triple greater than symbol here, and you do not get that one replicated. So we're going to zero those bits out. We needed this for some of our own internal implementations of our numbers. Next feature we had to add, we built this in .NET 6, was the idea of a preview feature in .NET. Never before in the 20 years of .NET had we introduced and included APIs in a version of .NET that were part of the build, that were part of the reference assemblies, but we didn't want you to use them yet. We didn't have a way to advertise these APIs exist, but you have to opt into using them. And that's what we needed to do. We started building generic math in .NET 6. We shipped it in .NET 6 as a preview feature. We stabilized it during .NET 7. The way we pulled this off is we introduced an attribute called requires preview features. By annotating APIs like number of t self as require and preview feature, we then have a Roslyn analyzer that hooks into the build context. And whenever you are referencing one of these APIs, if you are not into an opted in preview feature context, we actually throw a build error at you. We say you can't use this API unless you opt in to preview features either in your project file or by annotating your call site as the member that's containing this as requiring preview features itself. That way, if you stumbled across these APIs by installing the NuGet package for preview features, they'd light up, they'd be there, and you wouldn't accidentally use them thinking they were fully supported until you opt in. And in fact, between .NET 6 and .NET 7, we made drastic breaking changes to the API shapes of all those interfaces we showed you. So that was the first time we'd ever had preview features in .NET, and we've been using that in several other places since we did that. So the last couple of slides here, I just want to show you a couple of places within the .NET runtime itself where we've started to use generic math. Again, since this was just stabilized here in .NET 7, we just have a few places where we've started to use it ourselves. The heaviest usage, though, was across all of our existing numeric types. We're refactored everything to be based on these interfaces. But one no-brainer for us was in link, where we have enumerable.sum and enumerable.average. This was very similar to the standard deviation implementation that we walked through, where in enumerable, we had average overloaded across all the different possible primitive input types. And we had the same implementation copied over and over and over again with the same algorithm, just different types. We've refactored that to be based on an average of t source, t accumulator, t result, taking in an I enumerable of t source, returning a t result. We then kept the same public surface area, made the generic implementation private, and then we refactored the public surface area just to call into the private generic implementation. So you can see this reduced our code by, was it 830 lines of code we got to delete. That's best code in the world is the code you get to delete. And then during .NET 7, we also introduced a new feature for tar. Tomorrow I'll be talking a little bit more about our tar format and our tar APIs. But within our tar, we needed a helper for parsing octal values, and we needed to be able to get a variety of different output types out of this. So again, being able to overload on the return value is a new concept that you get here with generic math. So parse octal takes a t, or parse octal of t will return a t from a read-only span of bytes as the buffer, where t is an I number of t. We're using some of the same functions you saw earlier, just slightly different form. Instead of create checked, we've got create truncating, where we'll just ignore or truncate the bits that don't fit within the space we need. And then we just perform the implementation for parsing that octet. So generic math and all the language features you saw here available today. .NET 7 released earlier this week, along with C# 11. The demo you saw me give was in Visual Studio Community 2022, which is the free edition. It's the one that I use all day, every day, working on the .NET team. It's available today. Really hope you'll go give .NET 7 a try. And I want to plug a couple of sessions. Iris Clausen, I think I saw her in the room before. She's got a session later today, C# with sugar on top. While this session here focused on generic math and some of the language features that powered it, Iris is going to talk about some of the other new language features in C# 11. I'm excited to watch that session. I hope that you'll see that as well. And then tomorrow, I've got another session where I'm going to talk about broader updates from the .NET Libraries team. What other libraries updates are included in .NET 7 that I want to make sure you folks hear about. So that's it for generic math. I really hope this is helpful, and I hope you'll think about how you can start re-implementing algorithms within your libraries, within your applications to reduce code and save yourself some bugs. So thank you, folks, very, very much.